Hi everyone, name's Fabio. I work as a product marketing engineer for Frontgrade Gaisler. We like to change name. Hopefully you remember Gaisler. Anyway, I'll be talking about the GR765, which is the component that we are developing right now. As you may know, we develop a various of computing devices that go from single core microprocessors or microcontroller to multi-core devices, all of them based on the Leon processor. Our most performant device right now is the GR740, which is a quad-core Leon 4 processor, and it has recently achieved QML QMV qualification, and it has also an excellent performance to watt ratio. So we have been looking at that, and we saw that there was some space for improvements. Just to clarify, this will be a very hardware-related presentation, so I hope I don't bore everyone here, but that's what I came for anyway. What we saw, first of all, is that we would like to use a package that has more pins so that no sacrifices are needed and more interfaces are available at the same time. Also, we saw that there is a need for different interfaces that go from, for example, DDR3 or 4 for RAM, NAND for storage, and high-speed serial link controllers. We also, as you may have noticed, the software vendors outside of the space industry typically do not target Spark, and that poses a limitation. And also that single-board computers that rely on the GR740 typically need also a companion FPGA. So after noticing all of this, we have been looking at developing our next generation SoC, which is the GR765. This device will be an octa-core processor with the possibility to select through a bootstrap signal between 8 LEON5 cores or 8 NOL5 RISC-V cores. The target technology for this device is a 28 nanometer fully depleted silicon on insulator, and we are targeting a 1 GHz processor frequency. Among the several improvements that we're making with this device, we have a DDR3 memory interface, which is very much fault tolerant, and they can deliver correct data even though device is having a complete failure and other devices are having SCUs. We also adding quad SPI and NAND memory controllers. And we are looking into including a secure element to provide secure or authenticated boot, and also an embedded FPGA for glue logic. We are targeting an IB count package, in particular 1752, which should allow many interfaces to be active simultaneously. So one of the questions that we get a lot is that why are we including two different instruction set architectures in the same chip? And the answer is threefold, I would say. First, why RISC-V? Well, we deem that a new class of processors requires a more modern architecture. And also the benefit with RISC-V is that enables new technologies by standardization. And I'm thinking about the hypervisor extension, for example, or also the vector extension. We have, with RISC-V, we have a growing base of third-party ecosystem. And we also have the possibility to attract talent that didn't work with the space industry, but have been working with the RISC-V in other domains, and to be able to reuse their skills in the space applications. Why we keep Spark? Well, we have an existing base of space-proven hardware and software designs that are compatible to Spark, and therefore a very mature ecosystem. together with a very large accumulated know-how in the industry. So we have a software compatibility with all their LEON devices, and therefore Spark will keep being there. With the GR765, we are having both in the same SoC. We feel that both the architectures are needed by the industry, and this allows us to have a very fast time to market for our RISC-V core, while keeping the Spark architecture active. And also we have a minimal silicon overhead, as the processors will be there, but the rest of the resources will be shared. One more improvement that we're making for the GR765 is the interconnect. We are looking at a striped interconnect with 4 HB buses where all the processor cores are connected to all the stripes. And we also have a support for larger address buses, and we are looking at 36 bits compared to 32, how it was for the GR740. The idea with this architecture is both to increase performance, but also to minimize the interference channels between the cores, as bus transactions that are going on one stripe can happen independently from what's going on the other stripes. Similarly, also the L2 cache has separate pipelines, one per stripe. And also the DDR3 memory controller has different HB interfaces and is capable of accessing different memory banks at the same time. Moreover, the RISC-V IOMMU ensures the partitioning of the IO devices in the memory map. So let me talk a bit about the processors. The LEON5 is the last of the LEON processor line. It provides improved performance over LEON3 and LEON4. And this improved performance comes mostly from the dual issue in order pipeline, which together with better branch capabilities and a new cache architecture provides a significant boost on performance. The LEON5 keeps binary compatibility with the LEON3 and LEON4. And we also be looking at improved fault-tolerant features, but I'll describe those in a couple of slides. When it comes to performance, we look at a figure similar to an ARM Cortex-A53 with a core mark score of 4.5. The LEON5 is instead our RISC-V processor. It's highly configurable, and it can be implemented in either 32 or 64 bits architectures. In the GR765, we are leveraging the processor in its 64 bits architecture, and we are including all the RISC-V extensions that allow you basically to run software that can create virtual machines that on their own can run operating systems without modifications, basically running in full virtualization. And it will be compatible with the OSA embedded RISC-V platform specification. Also for this processor, we are looking at a performance figure which is similar to an ARM Cortex-A53. What is peculiar with our processors is that there is no need for lockstep or redundant CPUs. In fact, we hide the handling of the radiation-induced errors and we handle them in hardware. So software developers don't need to worry that much about it. We protect the memory blocks using error correction codes. And for the LEON5 and NOEL5, we have a single error correction, double error detection code, which is coupled also with the patent protected scheme that we developed that also allows to detect 3-bit and 4-bit adjacent bit errors. That can be a problem for multiple bit upsets in some technologies. We also have an hardware scrubber built in into the caches that constantly can be enabled to scrub automatically the cache and therefore removes the need for manual scrubbing routines. The LEON5 and the NOEL5 are VHDL IPs and are distributed in our GRlib IP library, which is distributed on its own under commercial, but also under the GPL license. Therefore, it's possible to download it for free from our website to evaluate our processors. But sometimes not everybody likes to play with the FPGA implementation tools, so we also provide some FPGA bit streams that you can just download them, flash them on some of the boards that we have support for, and you can also download the debug and some software toolchains, everything from free from our website, and start playing. So moving back to the GR765 itself, the idea with this device is to provide higher computational performance and also an improved power consumption figure. We also have more timing isolation features due to the interconnect and to the different L2 cache. Also, we have improved functional separation features, and these I'd address in this slide, where basically the NOEL5 hypervisor extension, together with the advanced interrupt architecture and the I/O physical memory protection and I/O memory management unit, which are all standardized or being standardized right now by the RISC-V committee. All of these allows to group I/O units together with guests into virtual machines and separate them from each other. Also, it's possible to distribute hardware interrupt directly to the guest in the hypervisor. We are looking at having the same I/O MMU implementation for both Spark and RISC-V mode. And we're also developing the hypervisor mode for the LEON5. We are adding, most likely, an additional layer of protection to limit which devices are allowed to access which memory mapped units. This layer might be needed for the LEON5, and in that case will be available also for RISC-V mode. When it comes to the interfaces, we are adding many compared to the GR740. The most notable is the addition of high-speed serial link controller with also SerDes on chip. And this in particular is capable of supporting space fiber, but also simpler protocols such as WizardLink. We have a 12-port space-wide router with also the capability of directly route space fiber traffic directly into space-wire communication links. We are keeping the Ethernet controllers, but we're also adding a 4-port TT Ethernet switch. The CAN interface in the GR740 is changing to a CAN FD interfaces with also CAN open support in hardware. We're adding I2C and also some interfaces to have a simpler connection to companion FPGA, in particular an FPGA supervisor that is able to program and scrub silence FPGAs, and also an SoC bridge interface, which is basically a very simple parallel synchronous interface that allows to have the companion FPGA as a memory mapped device from the point of view of the processor. When it comes to software, we provide a complete ecosystem for our Leon and RISC-V processor. We have tool chains that go from bare metal to Linux, RTEMS, and VxWorks, and Zephyr. We have partners that provide hypervisor software like Xtradum and PikeOS or Xvisor. And we also provide bootloaders in the form of MakePron2 or GRBoot, which is flight qualified bootloader. We also have a set of tools which go from the GRMon3 debugger to the TSIN3, which is our instruction simulator, compatible with all the Leon devices. What is important is that the GR765 and the GR740 maintain software compatibility. To give you an example, Linux image that runs on the GR740 will run unmodified on a LEON5 ecosystem. Of course, some differences are there between the two cores, like internal processor configuration registers, and also some other things. All of these changes, we are addressing them in a software porting guide that it's part of our deliverables for this project. So it should be fairly easy to port the code from one device to the next one. We're also doing this large amount of work to support the save level of software in the RISC-V as is available today for the LEON5, for the Leon processors, sorry. We are doing a set of activities to make the software ecosystem for Leon better. In particular, for the GR765, we are looking at extending the T-Sim simulator to have for support the GR765 and have the same level as accuracy as we have for the GR740. We're also looking at porting the GR flight qualified bootloader to the GR765, and also looking at Linux support, like how to address the bigger address space, and also developing basic low-level drivers. GR3 is our debugger that we provide that supports Leon and Noel processors, and I think many of you that have been using Leon processor are familiar with this tool. What I wanted to bring up today is that we have released at the end of 2022 a major release of GR3. Instead, we have C and C++ source level debugging with all the features that you expect from a modern debugger that you get from a commercial tool. So you have line breakpoints directly in your source code, and you can see variables and so on and so forth. I'm getting low on time, so I'll be quick. We already made a test chip on with both the LEON5 and the Noel 5 in the same silicon, targeting the technology, which is 28 nanometer. We got the best performance we got for this device was 1 gigahertz operating frequency, and we already made some radiation tests on this device, and the coupling the technology node capabilities together with the new fault-tolerant features, we have seen that a product based on this device would be harder than the GR740. So this brings me to the conclusions. The GR765 is an octa-core processor supporting both 8 LEON5 cores and 8 RISC-V cores, with also DDR3 interface and high-speed serial links controllers. The component prototypes will be available at the end of 2024. However, already from the end of next quarter, we will be able to provide FPGA bit files for early evaluation. We are still doing some development, and some changes can still be addressed. So your inputs are most welcome. Thank you very much, and I'm over for questions.